Hey guys, it's Chili here. Welcome back to Intermediate C++ Tutorial 5. Today we're going to be learning about dynamic memory allocation. This is going to enable us to allocate very large arrays, the size of which we can determine at runtime. Let's jump right in. Okay, so our task for today is we're going to load a very large text file, a novel, into memory, and then when the user presses a button, we'll give them a small random excerpt from that, as long as they keep pressing the button. Seems simple enough, right? The first thing I want to do is I want to get this database code here out of here. I'll keep it in a separate function. We might use it again later, but for now we're just going to move it out of main. So I just put it in a function doDB like this, and we'll just collapse that. Now the next thing here is we're going to need the actual novel. I'm going to use War and Peace. I just downloaded that, called it warp.txt. It's about 3.3 megabytes, I guess. Should be large enough for my purposes. Now, I'll put the link to download this on the wiki page so you guys can download it as well. So now what we want to do is we want to load that file. We're going to open that file. So we open the file like this, and now we need an array in memory to store the characters that we load in. So we need to figure out how big that array should be, and that's fairly simple, right? We go to properties, we look at the size, the actual size, like this, and we say, okay, well, we'll go const expression int file size is equal to, and this number here, we'll get rid of those commas, and we want to add an extra byte for the null terminator if we're going to store this as a C-style string. Now, really, we don't need this extra byte, and the reason why is because when we load this file into memory, it's not going to be this big. Can you think why? The answer is because that file is going to contain the 2-character new line code, and when we read it in, it's going to be translated into 1-character new line codes. So the actual file in memory is going to be somewhat shorter than the file on disk because those new lines are going to be translated from 2 characters to 1 character. But just to be safe, we add the extra byte in case when there's 0 new lines in the whole text. So we'll do that, and then we're going to create an array like this, and now we've got to fill the array, and I'll just use get again. So the reading in code is going to look something like this. It's very simple. What I showed you at the beginning of the last video. Basically, we're just reading characters in until we reach the end of the file, copying them into the array. I is the index that we copy into the array. And at the very last one, we put a 0 for the null terminator. Now, the value of I at the end is going to be the number of characters actually written into the array. Excluding the null terminator. So we're going to output this and compare it with the size of the file on disk and see if it's the same or if it's smaller. It should be smaller, but we'll see. So we're going to run this. This seems to be a problem. Stack overflow. What the hell is that? Well, that is what is going to bring us to the topic of today's discussion. Now, to understand why we get that error, we have to understand the different ways that our data can be stored in memory. There are 3 main storage classes in C++. They're called automatic, also known as the stack, static, and dynamic, which is also known as the heap. And depending on how our storage space is allocated in memory, there are going to be, different rules, different things that apply. Those of you who have already watched my red pill video probably have a little idea about this, but I'm going to go over it anyways. First, let's start with the automatic storage class, also known as stack allocation. This kind of allocation is used whenever you create a local variable inside of a function like this. So we create, for example, this array here, car warp string. This is going to be created on the stack. This int I is going to go on the stack. This warp file object is going to go on the stack. In here, Chili database goes on the stack, and what that means is that all of the members of database also go on the stack. So this array in the database is going to go on the stack. This is going to go on the stack. Static one is not going to go on the stack because it's static, so it goes in the static place, and I'll talk about that in a second. But the vast majority of all of the data, all of the storage that we've been allocating, the variables, we're putting them all on the stack. That's where most of the things go. Now, each of these storage classes has its own pros and cons, so let's compare them and see how they stack up. See how they stack up. You get it? Because it's the stack. So the first pro of automatic storage is it automatically handles the creation and destruction of, variables and objects and shit. So when we create, for example, the warp file, it's going to handle all the memory bullshit for us. It's going to keep track of the memory. And when we reach the end of this scope here, the end of the function, it is going to destroy that object and free up that memory for us. It all happens automatically. We don't have to worry about it. Another pro of automatic is it only uses the memory as needed. So when you create a variable in a scope, it will be using memory for that variable. But when you leave the scope, it will reclaim that memory, which is different than static, as we'll see later. So the automatic, the stack storage is, in a sense, it's dynamic in that when you call functions, the amount of memory being used is going to increase, but when you return from those functions, that memory is going to be reclaimed. And the final pro is the stack is very fast to allocate on. It's basically instantaneous. Now, as for the cons, one of the major ones is the stack space is small. The capacity is small. You can really only get a few megabytes of stack allocation. And there we have the reason for why we're crashing, the stack overflow. What that means is that you tried to allocate more space on the stack than was available. So we tried to allocate, 3.3 megabytes on the stack, and that caused the exception because there isn't that much space available on the stack. So that's one major con for the stack. The other con for the stack is you need to know the size of things at compile time. So if you want to create an array, like an array of cars like this, you need to know that size ahead of time. You can't load the file, check the size of the file, and then allocate your array based on that size. No, you have to know it ahead of time. That has to be fixed when you compile the program. All right, now let's talk about the second storage class. That's static storage. So how is this different from the stack? Well, first of all, where does this actually come into play? What kind of code will use static storage? Well, probably not too surprisingly, static storage is used when you create a static member of a class. So normal non-static members of a class, their storage is going to be allocated on the stack once for every instance of the class. But static members aren't per instance. There's only one static member, and all the classes share that. So that goes in a different place in memory, the static storage section. Other things that go into static storage include your string literals. They go into a section of the static storage that is read-only. I explained this in the string tutorial. So these also go into static storage. And if you create a global variable, like let's say this one that's outside of any function in the global space, this will also go into static storage. I don't really do this that often because it's a pretty shitty programming practice, but I mean, sometimes I guess it makes sense. Usually there's a better solution. So those are the different cases for automatic and static. Automatic is your local variables. Static is your static member variables, your global variables, IC, and your string literals, and maybe some other stuff, but it's not that important. These are the main ones that are going to go into the static storage. And the static storage is allocated at the very beginning of the program, and it sits in memory until the program ends. It never changes size, hence the name static. Now the pros of this are you can have a large capacity for static. In 32-bit mode, it's like something like up to 2 gigabytes, which is much larger than, maybe the 1 or 2 megabytes you can get on the stack. The other benefit is that, again, it's fast because it's only allocated once statically at the beginning when you load the program, so it doesn't eat up CPU cycles to allocate this stuff. Now, as for the cons, one of them is it's always going to be taking up memory static storage. So for example, with automatic storage, you enter a function, you allocate memory for the variable, and then when you leave the function, you reclaim that memory. But with static, you're always taking up that memory no matter what, whether you're using it or not. The next one is the same as stack, and that is that you must know the size of things at compile time, the size of your arrays, etc. And the final con for static is a programming style design problem, and that is that it's generally globally accessible. So static member variables can be accessed from anywhere in the program, and that creates big problems once you start to design, really big systems. It makes it much more difficult to figure out problems because anything can get at this memory. So now when you have to debug, you can't narrow it down. What is fucking up your data? Who knows? It could be anything because it's global, so anything has access. And finally, now we have reached the topic of today's video, the heap. So what is the heap and how does it differ from static and the stack? All right, let's step back for a second and take a look at a map of the memory of the computer and where things are stored in that memory. So when you load your program, you're going to load the instructions, the code of the program. That goes in the code section. You're also going to load static data like strings, and you're going to have space for other static data like globals and static members that you can change. Some of that, so the strings and other things are going to be read-only, and then, your globals and your static members, you're going to have a bunch of non-read-only stuff here. Then you're going to have your stack space, and it's not very much space, but this is where most of or basically all your local variables are going to be stored in. So when you enter a function, space is going to be allocated on the stack for the local variables of that function, and then when you leave the function, that space is going to be reclaimed. If you try to allocate too much space on the stack, you're going to go past this area, and you're going to have what's called a stack overflow. Now, the size of the static data section is fixed, and the maximum size of the stack is also fixed to a fairly low amount. Static data you can have quite a bit in here if you wanted. But the heap isn't really fixed at all. You can have basically as much of this stuff as you want. In 32-bit mode, obviously you can only have about 2 gigabytes. But if you're in 64-bit mode, the sky is the motherfucking limit. So how does heap allocation work? Stack and static are reserved when you load the program, but the heap is very dynamic, and you have to request it from the operating system, basically. So here's how dynamic memory allocation works, heap allocation. The program says, okay, I need, let's say, a megabyte of space to store some shit in. And so it says, okay, well, operating system, do you got like a megabyte that I could use? And the operating system's like, yeah, dude, no problem. Here's what I'm going to do. I'm going to give you this megabyte right here, this space in memory. And so the operating system reserves this space for your application, and it gives your application a pointer to that space. So you call a function asking for space, and the return of that function is the pointer to the space that you requested. And then what your program does is it creates a variable on the stack here, and this is a pointer. So it's now got a pointer, and it stores the address of this memory using the pointer. And so now this pointer is a handle to the dynamically allocated space that you requested. And now you can use this pointer to load and store data from this space in memory. It is your memory. It is on the heap. And when you are done with this memory, you call a function again on the operating system, and you tell the operating system, dude, thanks for the megabyte. I don't really need it anymore. You can have it back. And so you pass the pointer to the memory, and the operating system says, okay, good. I'm going to take that memory back. You don't need it anymore. Maybe I'll give it to someone else if they need it. Yeah, no problem. Now in C++, the way we allocate, the way we request that memory is with a special keyword, an operator called new. And there's also an operator called delete, and that is how you free the memory when you're done with it. Now, the major pro of dynamic allocation is that it is dynamic. the size is determinable. You can determine the size at runtime. You don't have to know it ahead of time. You can decide when you're running the program how much you want, which is not possible with static or automatic. Another pro is obviously you can get a lot of memory this way. You're not limited like you are on the stack. Another sort of pro is that the memory allocated with new can live beyond the function, because when you allocate something with new, it doesn't get destroyed when you leave the function. It only gets destroyed when you call delete. So you can allocate something inside of a function and return it from that function, and the thing outside of it can still access it. You can't do that with a local. If you allocate something inside a function and you return a pointer to it, the pointer is going to point to nothing, because once you leave the function, that shit is destroyed. But that doesn't happen with dynamic allocation. So this is a kind of a pro, but it's also a con, because it can live beyond the function. So if you don't keep track of your shit, you're going to have shit that's living when it shouldn't be living, basically zombie memory. Now, as for the cons, first of all, we have to keep track of the pointers. So when we call new and we get a pointer to a block of memory, we have got to keep track of that. We can't lose that pointer, because if we ever lose the pointer, we will never be able to find that memory again, and it'll just be chilling out in there like a turd in the punch bowl, wasting our memory. Another problem, which is kind of related to the one above, is that you must manually free the memory when you're done with it. And you'll see, new programmers making the mistake of continually allocating new dynamic memory without freeing it when we're done. And what you'll get is a program that gradually consumes all of the memory on the computer and then crashes. And this situation is called a memory leak, when you allocate memory and then you lose track of it and you never free it afterwards. You're leaking memory. The final con is that dynamic allocation is slower, because you've got to communicate with the operating system and request memory and stuff like that. So it takes a longer time than, stack allocation or static allocation. It's not a big deal. We're not going to worry about it for the time being, but it is something just to keep in the back of your mind. Dynamic is slower than allocating on the stack. All right, now filled with this knowledge about heap allocation, let's allocate something on the heap. Let's do it. So we're going to start off with a simple situation of allocating a single object on the heap. Right now we are allocating this database object on the stack. How do we allocate on the heap? Well, we're going to need a pointer. The pointer is going to hold the address to the allocated object. And now we got to set that pointer to something. So we got to request basically the C runtime to create something on the heap for us. So we're going to go new and chili database, and that's it. Now we have created a new chili database on the heap, and this DB pointer now points to our database. Now, because it's no longer a stack object, it is a heap object, a pointer. Now we have got to access these members using pointer notation. And that'll look like this. We just replace the dots with these pointers here, and everything should work fine. So let's quickly just comment this out, and we'll call the function doDB, and we'll see if everything works the same. And so we'll add something, we'll add a name and a value, and add a name and add a value. And we will print, and everything seems to be working fine. Beautiful. There's only one problem here, and that is we allocate this memory on the stack. We get the pointer to it. Great. But we never free the memory when we're done with it. Now, when the program ends, all of the heap allocated memory will be freed. So you can never leak memory and have it just permanently leaked until you turn the computer off. When you quit the program, it will all be reclaimed. But even though that is the case, you should still free the memory. Just bad programming. If you ever have a new allocation and there isn't a matching delete somewhere, you are a fucking piece of shit programmer. Well, I mean, there are exceptions, but in general, fucking just free your memory. And the way you free it is you just go delete and DB. And then there you go. That is going to free the memory that you allocated. And if we run that, and I just quit out. No problem, no errors. Everybody is happy. So always, always, always delete everything that you knew. If you knew it, you got to delete it. This is the main lesson of this tutorial. Fucking delete your shit. I'm gonna be very angry. All right, so that's how you do heap allocation for this object. Would I ever do it? No, because this object is this object is small enough to fit on the stack, and the stack is faster, and the stack requires me to do less bullshit. So I would never use the heap for this, but this is just an example. Just an example. I'm gonna undo it all now. All right, that's better. Back to normal. Now, here's an example where we do want to do heap allocation. Why? Because we're going to bust our stack wide open if we try to allocate this bullshit on the stack. So, how do we allocate an array on the heap? Well, again, you have to have a pointer that is going to be a handle on the allocated memory. So you create a pointer to string, and it's equal to new car, and then you just use the square brackets. You say, give me an array, a block of characters in memory. How many? Well, I guess I want file size amount. And there you go. Now this pointer is going to be pointing to a block of memory of the size that we requested, hopefully. Now when you're done with that memory, again, you delete that shit. Now deleting an allocated array is a little bit different than deleting an allocated single object. So keep this in mind. When you delete an allocated array, you got to do delete. And then you've got to do the square brackets, just empty square brackets. And then you put the pointer name, which is warp string. Where's my warp? Where is my warp underscore string? There it is. So this will delete the allocated block. Never forget, if you're allocating as a block of memory, as an array, you've got to delete as an array. And if we run this shit, we get our output. This is the actual number of bytes read in. And if you compare that to this, you will see that the number is smaller, 32933359. So the actual amount of memory used is somewhat smaller than the size of the file, again, because of those translated new lines. A little bit of waste, a little bit of overhead, but it's not a big deal. I'm not going to worry about it. All right, so now that we are able to load our novel into memory, we can tackle the original problem that I set out for us. And if we quickly code that up, it'll look something like this. I just did it off screen because it's not really important for this lesson, and it's pretty simple. You guys can figure this shit out. Just some random number generation to get the start of the snippet size, and then we prompt the user for some input, and if they want to read a snippet, then we just loop and we put a bunch of characters from a random section onto the console. We press Q, they quit, and we will free the memory and leave. So if we run this, I included, by the way, if you couldn't guess, random for this as well. If we run this, now we can read a snippet or quit. If we hit R, we get a snippet of text. There are some garbage characters in here. This is because the encoding of this text file is Unicode encoding, UTF-8, which is similar to ASCII for your normal characters, but you're going to have special characters that kind of turn out to be garbage. But yeah, we can keep reading snippets, random snippets of the book as much as we want, and then we press Q and we quit. So this dynamic memory allocation, this heap allocation stuff, this is great. It allows us to allocate nice big arrays. But you might be saying, Chili, I mean, I could allocate big arrays with global variables. So what's really the benefit here? And the benefit is that we can do this dynamically. So let's say now that instead of fixing it to just loading this one file, we could load any text file we wanted. So what we could do is we could prompt the user for a file name, and then we'll read in the input from the console. And then we can load the file name that they gave us, and we can check the size of the file. So we can do const int file size. Notice this has to be const. If we can't make it const expression because it's not going to be known at compile time. So we can go file size is equal, well, first we can go, let's go warp file dot seekg as 0, and std ios base end. So we'll seek to the end of the file, and then we'll call tellg, warp file.tellg, and this will get us the size of the file, and then we can load with file size +1, give us extra space just in case we need it for the null terminator. And then we can load in as normal, and then we can erase down here. So this should work, I'm thinking. Oh shit, almost forgot. We seek to the end of the file. We've got to seek back to the beginning before we start reading. So we do warp file.seek g0 std ios _ base and beginning beg. So this will seek to the end, get the file size, seek to the beginning, and then allocate the memory, read the shit in, and then do the bullshit. So we do warp.txt, and then we can do R to read a snippet, RQ to quit. And that works fine. And now we can load in different files if we wanted to. Now we can really see how this approach shines when we look at what happens when we try to load a different file. So I've downloaded another novel called, I shit you not, Ragged Dick, which, I mean, you know I'm going to be downloading this one, right? So I got now a file dick.txt, and if I run the program and I enter the file dick.txt, read a snippet, now I can read about the Ragged Dick. And the amazing thing about this is, okay, so sure, you can allocate a big ass array globally, and it'll be able to fit any book you want, basically. But here's the thing. Let's say I allocate, a 10 megabyte array in memory that'll fit any book I want to load. If I'm loading Ragged Dick, right, that's only like 200K. I'm wasting a shit ton of space with a global static array. Whereas if I allocate my array dynamically based on the size of the book that I want to read, then I'm only using as much space as I need and no more, which is a lot better, right? So for stuff like this, dynamic allocation is awesome, and static allocation can suck on my balls. All right, let's take a look at the homework now. I got an interesting one for you guys. It's not going to be in the console. We're going to revisit Meme Sweeper. And when you start the game, you're going to start off with this menu here, small, medium, or large. And then when you click one, the game will start. And when the game is over, like this, you can click again, and it goes back to the menu. Now, depending on which of these options you pick, you're going to start off with a different sized meme field. And the way we're going to implement that is I'm going to get you guys to implement that with, new and delete, dynamic memory allocation. Now, I've got good news for you. The good news is that you don't have to implement this menu. I've already implemented the menu. So all you're going to do is you're going to go into the repo for Meme Sweeper. You're going to right click on this, the one that has this tag here, i5 homework start. Right click that, and you're going to create a new branch. And then you're going to branch off from this commit here with this tag, and you're going to do your shit from there. Now, in there's already a bunch of code for the menu, so you don't have to implement the menu. But what you're going to have to do is you're going to have to see how the menu works, because I'm not going to tell you. That's part of the homework, is to be able to orient yourself inside of a code base. You should already understand the basics of Meme Sweeper if you've been following the tutorials properly. Now, for this homework, you're going to have to figure out how the menu works and how to interface with it. You don't have to understand the whole thing, but you do have to understand enough to be able to interface with it. And then you're going to have to implement the dynamic allocation of the meme field. So again, the homework is really two parts. Part 1, understand how the menu works, and part 2, implement dynamic allocation of the meme field. Understanding how other people's written code works and how to orient yourself inside of a code base and get yourself up to speed is a super important skill for a programmer. So you need to fucking practice that, and I am going to give you a push in that direction. But that's it for tutorial 5. Thanks for watching. I hope you enjoyed the video. If you did, please click the like button and leave a comment. It helps me out a lot. And I will see you soon with some more C++.